Welcome to the office. I want to take a really quick look at the definition of a homomorphism. Again, this is a term that we've already heard before, right? The homomorphism property. So we just want to kind of make a statement that, hey, look, here is a formal definition of a homomorphism, right? As I said in the last video, it's just a mapping that has the homomorphism property. That's it. It preserves the operation. So if phi maps group G into a group G prime, so it's not necessarily covering, though it could be. Anyway, it's a homomorphism if it satisfies the property. The image of a product is the product of the images. So using multiplication notation here. And for a very, very brief example, it's worth pointing out that for any pair of groups, G and G prime, for any two groups, there is always the trivial homomorphism, which maps all of G directly to the identity element in G prime. So cool, right? Nothing fancy. This is essentially saying in that same sort of representation that we had in the previous video, here's G, here's G prime. If I have a bunch of elements, whatever they are, I might have a bunch of elements over here too. Doesn't really matter. But if this is the identity, then the trivial homomorphism is the homomorphism that just sends everything to the identity. And of course, since phi of A, B is equal to E, but that's just E times E, which is phi of A times phi of B, right? So it clearly has or satisfies the homomorphism property. So it is a homomorphism, that is. Anyway, a simple example along with a definition. That's all I really wanted to share. So thank you for your time. Let's take a look at some actual examples, or some more interesting examples rather, in our next video.